so homework 3 is due Friday. Yeah, Friday. That's including the late days. Homework 2 peer reviews went out. If you didn't get one, we didn't get a pull request from you, probably. Talk to us about that. Please finish those today. Then the TFs can get graded. We won't do that for homework 3. Do keep in touch with your TFs about final projects. If you hit something where you're spending if you've hit anything, any sort of problem that you think we can help with, first try to solve it on your own, of course. If it starts to take too long, you don't feel like you're making progress, don't fall behind, all right? You can send them email. They can, maybe find something and point you to a web page that you can read on your time, but don't let any sort of technical issues or questions about how to approach a problem. If you don't have an idea, talk to your TF so that you don't get stuck. And a reminder, there are no late days for the final project. All the due dates on the final projects page of the course website are firm, and they're midnight of whatever day they list. Okay, today, I want to talk about cache oblivious algorithms and data structures. It's a topic that's interesting. It's kind of an active area of research. It's useful to know in terms of both GPU programming and multi-core CPU programming. I'm not going to talk too much about multi-core. Almost everything I say does apply to multi-core. It's more just, we've talked a lot about caches and about performance and about how interactions with the cache in performant code are important. This is going to talk about some of the approaches to doing that when there are so many different hardware configurations out there. Things are changing all the time. You've got NUMA, you've got different levels of cache with different associativity, things like this. How do you deal with that? And one of the cool ways to deal with it is to say, I don't care. I know there's a cache. I don't care about any of its configuration parameters. I'm just going to take advantage of it. I'm going to write an algorithm that guarantees that I'm going to take roughly optimal, I'm going to use my cache roughly optimal. All right, so we're back in multi-core land. We have compute. We have caches that may be shared between the cores, but in general, we'll just pretend that each core has its own cache of some sort. And then there's memory. Access to the cache is fast. Regardless of what level, even when you talk about multi-cache or multi-layer caches, access to the first level of cache is going to be an order of magnitude, or usually an order of magnitude faster than access to the next level of cache, which would be an order of magnitude faster than whatever's below that. You can have memory. You might be doing out-of-core computations where you need to have you have disk underneath this for a very large amount of space. That's going to be an order of magnitude slower than memory. You might be talking about cluster where you've got your local drive and then some large networked drive that you access data from, and you cache some of that data. Again, another order of magnitude. We'll just work in this sort of two-layer existence for now, and we'll make some simplifying assumptions. We'll also assume that the cache is small and the memory is big, and the data that we're working with is much larger than the cache. Okay? Also, all access to memory is through the cache. When a CPU, a core, needs access to some piece of data from memory, it says, oh, I need this location from memory. It goes through the cache. The cache either has that piece of memory already, in which case it returns quickly, or it doesn't. And then so it goes into memory, gets it, and it stores it in cache, and any further access is there. The cache will already have that value, and up until it gets ejected from the cache because you've used too much other data. So when we access a new memory address that isn't in the cache already, assuming the cache is full and has been used for a while, right, it's going to have old values in it. We have to get rid of something to put that new piece in, right? We'll assume that the cache replacement policy is least recently used. So the cache has basically a priority or some sort of timer. When did I last access this? Each time we access it, that gets set to just barely. And whatever was used least recently is the one we'll get rid of. There are other choices that make sense, including, so most recently used. I mean, there are a bunch of things you could think about doing here. Most recently used is basically whatever I used last, throw it out, which seems like an odd choice. When might this be good? What if there's no reuse? What if I'm involving a filter, a fairly large filter across an image, or across a signal, right? If I'm doing a linear signal, I've got a big wide filter. I can just barely fit my filter in cache, plus a little bit of memory for data. I'm gonna read a piece of data, I'm gonna convolve my cache with, or convolve the filter with it, and I'm gonna read another piece of data. The least recently used might be my filter, right? And then I'm throwing away something I'm gonna need in the next iteration. If I use most recently used, it's probably what I loaded last, which I'm never gonna look at again, right? As I slide this filter across, I actually do wanna throw away something I loaded very recently. I'm gonna read it once, I'm gonna use it, and throw it away. This is the best. Last to be used in the future, right? The piece of data in my cache that I'm gonna need the farthest in the future, right? Possibly never. Unfortunately, we don't usually know this. Right? We can't predict what our programs are gonna do always. Sometimes we can. But it turns out actually, and this is an old result, this is like from the 60s. LRU is the least recently used, which we'll assume, and which is the standard in most cases, is no worse than 2 times, like that's a hard 2x times the optimal. I don't know the details of this proof, but we'll just assume LRU because it's common and it's not so bad. Right? We'll be within even if there were a better caching strategy, we're not gonna be too far off. All right, when we talk about cache and computations and when we're interacting with the cache, we'll assume that we have a cache, we're just gonna assume one level of caching. It has some width, usually 64 bits, whatever, and some number of lines. And we'll assume, there's some L for our cache size. Computation is free. Once it's in the cache, computation on it, we'll assume that we're not gonna be doing very computationally dense, but even on fairly computationally dense problems, they're gonna be limited by cache. Cache hits are free. The only thing we care about are memory accesses. And we'll ignore all the weird hierarchical stuff or NUMA stuff or anything like that when we do any sort of analysis. We're not gonna do any analysis of algorithms here, but this is the usual thing they do for cache oblivious analysis. All right, let's look at a few example algorithms and their cache oblivious implementations. We'll start with just matrix multiply and transpose, sort of classic, talk about binary search. There are others. We're not gonna go into those in this class, but if you are working with anything like sorting very large data sets or sorting when you need very fast performance, hash tables, priority queues, any of these, cache oblivious versions do exist, and they're often very performant even in their simplest form, sort of unoptimized. All right. One weird trick for cache obliviousness, divide and conquer. We take the computation that we're gonna do, and we find some way to break it down into subproblems that are exactly the same structurally as whatever the larger problem is. And then we just make sure that we can lay out memory and memory access to match that algorithmic path, right? You may have or probably have dealt with divide and conquer computationally before. In this case, we're gonna use that divide and conquer strategy to also set up our memory access patterns. And it'll turn out that this maps very well to caches and cache behavior if we can do this, which is not always the case. Yes?
So what do you mean by divide and conquer? Like, let's say you have an image or a matrix multiply. You're saying that you're going to break down the matrix into parts that you can cache.
That's a very good question. Let's talk about it. How do we break this down? How do we divide and conquer? It's problem dependent. It's not a general, it's a general framework of ideas for how to approach large problems. We'll talk about the matrix multiply in particular. How do we break this down into subproblems? So matrix multiply, right? It's just we're taking 2 blocks, we're multiplying. The red element is the dot product of those values and these values, right? And any position in here, you take the row of the output and the column of the output, and you take the dot product of all those values, okay? So if we do this in the naive way, just nested loops, it's n cubed, where n is the size of the edge size of the matrix. When we read out a row for this dot product, that's cache coherent, right? That's gonna be very, if we just iterate across here, right? Taking values, reading that value, multiplying it by that value, reading that value, multiplying by that value. These values are cache coherent. So once we fetch this first value, we can basically assume that for a long time, our other fetches are free. Right? There are no more memory accesses to get the rest of that row. But here, that's not the case, right? We read this value, and we assume that it's laid out this way in memory, like a usual image. This value is separated from this value by the size of our matrix, which is probably quite large. So each of these is a new memory read. Is that clear? Right? We get good cache behavior on the left, poor cache behavior on the right. Basically, worst cache behavior. Yeah, we assume it's, for now, in the default case, right, we'll assume this is cache, this is contiguous. Right? We'll change that. So how do we decompose this problem into something that's self-similar to take advantage of this? If we look at the matrix, so we'll look at submatrices, basically. We'll break it down into these 2x2 submatrices. We'll assume square in power of 2 for now. There are generalizations of this that are not difficult for rectangular matrices with different widths and heights. We'll look at these 4 submatrices. That upper left block of the output, that's not a single value. That's multiple values. So if this was a 1,000 by 1,000 matrix coming in, that would be, or coming out, that would be 500 by 500 values. That submatrix is equal to the matrix products of these submatrices. Right? So it looks like this. So the first term is the upper left of these two matrices, and then just their matrix product, and then the upper right and the lower left. That's clear from the definition of matrix. It's not, if you assume that that was a 2x2 values, this would be just the actual, how you would actually compute that value. It works the same for submatrices. So when we do that with the full 4 outputs, we get these 8 matrix multiplies and adds. And this is the same number of multiplies that we started with. If you write it out as the matrix product, if you do this, it's not more efficient, right? There's the Strassen method, which then computes some other matrices that are, basically reduces some of the matrix multiplies through some algebra. That's not what we're talking about here. We're just breaking down the matrix multiply hierarchically and not trying to optimize it in any other way. Right? So we do this, and we keep subdividing, right? Now we've got okay, how do you multiply 2 matrices? Well, let's subdivide and then down until we get to just one value or something small where it fits into cache, where A, B, and C would fit into cache. Now, if we use that default memory layout of linear across, that'll never happen, right? They don't fit in cache because they're not on the same cache line in memory. But that's fine, right? What's our trick? Let's find a decomposition where they could fit into memory and then organize the layout of memory so that they do. So we'll do that. We'll use Z order, we'll use Morton order, anything like that, right? Where we lay out the matrix in this, the matrix elements in the Z pattern and keep doing that decomposition until eventually small squares of the matrix would fit in cache, and if you look at the pattern, are contiguous in memory. Does everyone see that? By reordering this, exactly the same as the computation that we just laid out, right, with this hierarchical recursive definition of matrix multiply, eventually we'll subdivide down to the point where this and this both live in cache. And then all of the reads, we do one read here and one read here, and all the multiplies together under our cost model, there's no memory read. It doesn't make the 2 matrices close in memory. What it does is, so as we subdivide, right, eventually we're going to get down to at some point, we're going to subdivide. And one of these submatrices, actually maybe it's better with a picture, would fit in cache if only it were, contiguous, right? At some point, we're going to be multiplying this block by this block. And we only have, eventually we're going to get it down to 64 values or something like that. Right, right. And then any of the recursion that happens below that doesn't add to our cost, right? Once we read this block and read this block into cache, once they both fit in cache and our C output, once all three fit into cache, under our cost model, right, which is only memory reads, compute and cache reads cost 0. We can do whatever we want multiplying these two together, and it's for free, right? Yes? No, no, just the separate ones. Just once I get down to, I'm going to recurse on that and then recurse on that. And once I get down to this point and this point, once I'm doing these two parts, they still are not, they're not small. They're still, could be, 8 by 8 or something. Once they both fit in cache, any computation I do below that with this, and this output is free under my model, right? No memory reads. Because to compute the product of this and this, I don't need to read any other memory. So once I get that and that and that into cache, everything else is free. So it's just making sure that I can get to that point.
Why does Z-ordering help you though? Does Z-ordering depend on like the magnitude of the element?
Why does Z-ordering help? It doesn't depend on the, Z-ordering is by position, not by, let's go to the Z-order picture.
You're sorting by the
Position. This is the layout that I'm going to switch to in memory. So no longer am I going to store them, horizontal rows of the matrix. I'm going to store them in this order, where first element is still the upper left, but then I follow this path. So this is the linear layout in memory, that recursive Z order, which is exactly the same order that I would get if if you look at the order of these computations, actually no, that doesn't work. Well, this one, and then this one and this one. If you look at those two rows, as I recurse, just looking at the A's in those two lines, that's exactly the order I would get for my recursion anyway. Yes?
Where is the trade-off? Like the other two like ordering your memory in the margin.
So the trade-off is index computations. Finding out where to store things, right? Where, if I want, it's easy to figure out if I want, a particular position within an image, like we did in the OpenCL homework. It's easy to say, okay, well, that's just the row times the width plus the offset, right?
And what if I want to add a column?
Well, if you want to add a column, that's going to be a pain in either case, right? That's going to be a lot of, so we're just talking about costs of memory reads. Everything else is free. And so adding a column or something like this it's going to be as bad in this world as in, I think. Adding a column could be worse in this case, right? Adding a column, if they're stored linearly, right? I'm going to allocate a new matrix, right? And then I'm going to copy values from one. All right, if I'm adding a column, I've got a matrix stored here, and I'm inserting a column here, but all of these go here. Adding a column is going to be pretty, if things are stored linearly, is going to be very nice in terms of cache coherence. I'll read that block, and I'll write part of it here, and I'll write part of it here, and then I'll read some more, and then repeat. That's going to be pretty good cache-wise, right? I'm going to read a block, and I'm going to use a bunch of it. I'm going to write a block, and I'm going to write a bunch of it. Then I'm going to move on and never touch that again. In this case, it could be quite painful, right? Because when I try to read, right, in this case, a column or even a row, copying a row from one to the other could be all over the place cache-wise. So hopefully I won't have to do that, yeah. It's a good question. This is going to be more useful when you're constructing, well, you might convert between them, which could also be somewhat expensive. But it might be less expensive than the default case is something like n squared memory reads, order of. And that may not be that bad compared to this. It may be actually worth it to translate between. But you'd probably just store your matrices this way. Usually when you're using matrices, usually you just have them. You multiply them together, you get some new matrix, and the memory layout doesn't ever change. There was a question over here, or maybe it's gone now.
So if you go to the next slide again, sorry. Oh, sorry. So the A's, sorry. The A's, like in the first and third row, follow the order. But the B's are like every two, right? So then you're doing a loop over the Z order of the B's, and then the loop over
Right.
the order of the A's.
Yeah, so the layout is maybe, you get a Z order if you look down the sort of when it first appears in the computation.
But you still have to like load, you can't like have A11 and A12 in memory at the same time.
Right, that's exactly the model. Right, at some point, A11, I'm going to recurse. Each of these I'm going to define by, okay, subdivide until I'm down to, until I'm down to just a value. It's going to look like, I start off with, we'll just draw one matrix. I start off with a very large matrix. And then I say, okay, well, I'm going to deal with these small matrices. And eventually, so at some point, right, if this fits in cache, even if I have another subdivision below, all of this, everything that gets down into this subdivision, once I get to this point, is free under my model, right? Because we said this, the one it's being multiplied against, and its output all fit in cache. So anything that I do, including recursion down to lower level, finer subdivisions, within that area is free in terms of memory reads, okay? So yes, when I'm looping across this, I may be able to do, or as I'm doing this recursion, I may do that, and it fits in cache at some size, and I finish. And then I go on and do that, and I throw out everything there. And when I get here, I have to load it back into cache. Right, if that just barely fits into cache, and then I go and do this, and it ejects what was here, right here I don't get to reuse A11.
So wouldn't it just be more efficient to do A11 and use it twice in a row, rather than like get U11 and use A11 twice, and then do the second row with A11 twice?
Possibly.
But then it's not the Z order.
Right, but it's not the Z order that we're using, but I have to order by A or B or something. I have to order by something. Yes, I could reuse this, and if I knew that my order were a particular, I might do some. Where was I looking? There's also reuse here that could happen. There are some things I could do more efficiently here. I could probably reduce it by, yes, computing these and these, but then I have two different outputs. Right, if I try to keep A11 around to use it here, then I have to use a different C12, and so I have to store C in cache as well, right? C is going to be involved. A, B, and C are all going to live in the cache at some point. When I get down to a small enough space, A, B, and C all live in the cache. Right, and so if I start trying to do tricks where I keep A11 around, then I also have to keep C11 and C12 around. But then I'm going to have to read it back to add to it. We're back in a land where we don't have adding. Well, so you're talking about like atomic adds? Yes, atomic adds are slow. They might happen on special hardware that's near the memory, and there are CPU architectures proposed where you can do things like add this value to memory. But in this case, we don't have that. So we have to load C in even to write to it and to increment it. So we read it into cache. So yes. Yes, if we could write, then we could do probably a better, if all of our writes to C were increment by this value, and we could do that without loading it into cache, there's probably a better way we could lay this out. But if we have to read C in to increment it, then it's unclear that we can, I mean, maybe. So when we do this, and we won't go into the analysis, it reduces it from n cubed plus n squared memory reads, which is the default under the cache model. That's how many, because n squared is basically the A matrix, n cubed is the combination of the B matrix and how many times we repeat it. Memory reads to something like the square root of the number of lines divided, which is not insignificant. I mean, the caches are quite large. If we have L cache lines. And I think that may be, there might be a proof that that's roughly optimal. It might be slightly better. You might be able to reduce it to L. L might be the upper bound. Any case. Let's talk about transpose. Right? Again, reading that row, cache coherent, basically free after the first read, all in the same cache line. Writing it, all in different cache lines. Exactly opposite what we would like. If we use the same memory layout, though, then eventually when we subdivide down, right, we do the same subdivision to transpose an array. First transpose this quadrant, then and recurse down there. Eventually, these both sit in the same cache line if we're using the Z order for input and output. And that's perfect, right? That's, oh, that should be L. No, actually, it's just B. B is the number of bytes that we read at a time for a cache read, compared to n squared. Yeah, n squared, because the output we read in a very poor. So that's basically perfect for transpose. And any space-filling curve here probably works. You can use Z order, which is easier to compute than Morton. I don't know if there are any competitors besides that, maybe Spiral or something, but I don't think that's good. All right, let's switch. Binary search. We're looking for the green element in this array of sorted values. Before I go on, anything more about matrices? Okay, good. This is just number of memory reads. Well, so n cubed for the matrix multiply. It's not, it's n cubed memory reads, not n cubed operations. It's n cubed because you read the, in the default case, you read a column of B, and right, you read one row of A, and you read every column of B. To read every column of B, if it's in that, if it's in row order and you're reading columns, is n cubed. Well, to read all of it that many times, right? That's where it comes from. It's because you read B so badly. I mean, you could transpose, but transpose again ends up costing more. If you just need to transpose, you can do it efficiently this way, though. All right. Binary search. Okay, so we're looking for the green element. This is a sorted array. We start off with, all right, we'll look at the middle value. Depending on whether it's larger or smaller than the value we're looking for, we hop somewhere, right? We hop, maybe say, okay, well, it's not here. So we take half our array size and we shift over. Is it there? No, it's smaller than that, so we hop there. We're gonna hop back and forth with successively smaller steps until we get to the element that we care about, that we're looking for. Very poor cache behavior, right? Read a value here, and with that we're gonna read a block, a cache line, and then we use none of it. We hop someplace else and read. Assuming this is a much larger array than what I've drawn here, we're gonna read a bunch of values there and use basically none of it, except for one value. Hop again until we get to finally to the value that we care about. There are probably, if this were a very large array, we might have a lot of hops, and when we got near the value within such that, the last log n, where n is the number of elements we can read into one cache line, those would be free, because we'd have the neighborhood of the green square in cache, and we could hop back and forth very quickly. But the tree is probably much taller than that. All right, we're going to spend most of our time up in read an element, read a cache line, read one element from it, throw it away land before we get to the bottom. All right, we read all of these values. We used one each time. Each one cost us a full memory read. And if we search for a different, if we look at this, if we were searching for that green square, we would have read the same elements, right? This pivot, this halfway point, every time we start a search, we read that element. And then there's basically a 50% chance that we're going to read that element or its complement over here. And then the same thing here. That one is quite likely to be read for all the searches to the left of it. All right, we're going to read these sort of key points multiple times in our binary search, or every time we do a binary search. There's a certain density, or certain elements are very important to the binary search. The one in the very center, the one at the quarter mark, the 3/4 mark. How could we fix this? How can we fix the memory layout? We could also, instead of looking at the array as a, horizontal value, just an array of horizontal values that happen to be sorted, there's sort of a binary tree that we can induce from this, right? If 8 is in the very center of the tree, basically the same array that we just showed, if we read out the leaves and the nodes in order, 1, 3, 4, 6, right? It's sorted. 8's in the center. That's where we start our search. And then if we were looking for 4, for example, we'd hop over to 3 with this many hot elements in between. It's larger. We jump this way 2 elements because there's 4 in the center and then 4. And so instead of hopping around in a linear matrix now, we're just traversing a tree. It's still stored in an array. This is just how we're going to draw it to look at the behavior of the algorithm. Right? We would like all of the top elements of the tree to be near each other. Because every time we search for a value, we're going to read 8. And half the time, we're then going to read 3. And the other half the time, we're going to read 10. So when we read 8, we'd like also to get 3 and 10 into our cache. Right? Because then we'd have them there, and the top half of our search would be for free under our cost model. Right? If we can load a bunch of the top of the tree into memory with one memory access and have it in cache, and we can do the whole search down to a subtree for free in terms of memory accesses. Is that clear? What's going on there, what I'm arguing? And we could repeat this process, right? Divide and conquer. Once we have the ability to do that, to read the top of the tree into cache, whatever trick we used for the bottom. And then all the searches after that, right? If these are all in one cache line and there's more tree hanging off of them, the top, we read one cache, we find which subtree to go into for free. So, how do we do this with an actual binary tree or actual array? So we have a binary tree of height h. We'll assume that it's complete, so it has 2 to the h nodes within there, approximately. And we'll cut it at half its height. Right? And what we'll do is we'll put all the top 2 to the h over 2 values in one set and all the rest in another set. This is my favorite data structure just because of its name. That's someone's surname. It's like Thomas Van and de Bois. Usually just called VEB trees. So we cut it at height h2. We now have this big triangle on the top that's everything above that cut line, and then a bunch of sub-triangles underneath. And then we do this recursively, and we store each triangle contiguously. So the top elements all are in one block of memory. Then each subtree, indexed from that somehow, is also stored contiguously. So when we search, once we subdivide this enough, such that the triangles all fit in one cache line, then when we load that, when we search the top node and decide which way to go, and then the node below that, everything within that orange triangle is free, right? Because we've read it into memory, it all came in at once. We can decide which triangle to recurse on. And then each of these steps is one memory read. Okay. You can do these, you can build the trees themselves, that's inefficient. You can actually do the index calculations in the linear list as well. Yes? Each triangle has n elements. It's one memory read because we're gonna take our tree, and instead of storing it in order for a binary search, we're gonna store it in the VEB order. Which means that all of the triangle at the top is gonna be the first part of our tree. In some, swizzled in some crazy order that's not the same as sorting. But if we do this recursive subdivision of the tree, and then make sure that we read out the top elements linearly into the first block of memory, the next triangle into a block of memory. When we read the top node, right? Let me go back a little. Right, this one. When we start our binary search at node 8, we get into the cache. 3 and 10 are also going to be in that triangle, and possibly some of their children, depending on the size of our cache. When we say, is my value that I'm searching for bigger than 8 or less than 8, our next step, we compare to 3 and 10, they're already in the cache. So we read from memory to get the 8 and some of its children, and then we hop down those children to find where we need to search next. Some number of layers of the tree beneath 8 will be in cache already. Because what we're going to do, so we do when we get to this point, we store all the elements. The tree has exactly the same structure, hidden within here. All the elements in the top triangle, we read out first into memory when we do this reordering. If we were actually doing the reordering, you'd build the tree like this to start. And then after that are all the elements in that first subtriangle, and then the second, and the third, and the fourth. And you recurse down until it's just one element. And in that recursion, in that in-order recursion, when you get to that element, when you subdivide down to one element, you keep track of where have I last read a value, that's where it goes. Or how many computations have I done? How many nodes have I already read? Sorry, how many nodes have I already read? That's the position it ends up in the array. Is that clear how these end up now? So when I start searching in that upper triangle, it's one cache read, or it's one memory read. Cache has enough to do the entire triangle, and then I go to the next triangle and down. Yes? Eventually they will. So am I assuming that they fit into one cache line? At some point they must. I'm going to do this recursively until it's one element, and one element fits in a cache line. Yes? Do we stop when the triangle fits in the cache line? Cache oblivious, we don't know. Right? We're cache oblivious. We don't know where our cache line is. So what we do is we do it all the way down to one element, and whatever the cache line is, some triangle above that fits in the cache line, right? We don't need to know where that line is, because our computations, when we're searching the binary tree, when we're looking for which second layer triangle we should start searching in, all of our computations are confined to that upper triangle, right? Any comparisons that we do are only in the upper triangle before we go to the next level. So if this were actually cut into a bunch of smaller triangles, they'd still all be orange at the top, right? They'd still all be in cache. After we read the first node, we're going to read in some subtree of it. We don't know how much because we don't know the size of our cache or our cache line. We just know some of it will be there. And so when we start searching within that subtree, it's all free in terms of memory rates, right? It's already in cache. Right? So, suppose this is just about the memory ordering. Suppose this triangle would fit in one cache line, or cache. It fits in some useful piece of memory. if we do the work beforehand, or the memory reordering, to turn it into this, right? If we subdivide it once or however many times. The way the cache works is, if these are stored contiguously, all we know is that this can be read into cache. And so when we read this first node, even if it's subdivided further, it still reads this whole block. So we subdivide down all the way to this, or smaller. And if our cache is very large, it doesn't matter. We still read in all of this. And this is how much, basically, we get this much free work, right? However much however many layers of the tree we can traverse with using only one memory read. Whatever the size of that is, it may be, if we have really huge cache lines, right? When we read the first one, if we store in this order, we'll read this much, and we'll get this much free computation before we go down. So we don't need to know. We're cache oblivious. We know there's a cache. We just don't know how big it is. But this will basically optimally use it. At some point, the triangles are small enough to fit in cache. And any triangles smaller than that get loaded together anyway, right? Because they're all contiguous. That's the other thing. These, when we subdivide, they all go in the first block of memory for that triangle, right? And if there's some other subdivision, this goes first, that second, third, fourth, it doesn't matter if they all get read in at once. Does that answer the question? Okay. All right. The kicker is, index computations for this can be complicated, right? Figuring out where things go, you've got weird, like you cut off not half the tree, you cut off a small part of the tree in terms of total number of elements. Right, each of these triangles store the same number of elements each time we subdivide. And so the top triangle has a lot of children. It's not 2 children like a binary tree. It's something like 2 to the square root of the total the log of the total number or something. Index computations can be complicated, and yet this layout is competitive with B trees and other complicated sort of cache knowledgeable layouts in a lot of cases. In terms of other algorithms, you can search for cache oblivious whatever. Funnel heaps, which are good for sorting. B trees, there are cache oblivious versions of B trees. B trees by themselves are somewhat cache oblivious. These are used a lot for databases and file systems, things like that. Sparse matrix multiplication, et cetera, et cetera. And again, there are many cases they're just as fast as tuned. Right in there, you take this algorithm as described, implement it from, just here's my first implementation. I haven't optimized it at all. And it can be quite competitive with things that have been tuned to take advantage of the cache without any further optimization. And cache oblivious in parallel is just now, well, it's been going on for a few years, but it's still quite an active area of research. How does this start to behave when you've got multiple objects or multiple computational units with shared or without shared caches doing the same computation at the same time? Sometimes it works quite well, things like matrix multiplication. There are some trivial decisions about ordering that work to your advantage here. Sometimes not so well. All right, questions about cache obliviousness? Excellent. All right, so Friday, Adi will talk about transactional memory, which is sort of follow-on to the lock-free stuff, sort of a higher level thing. Monday, I'm open to suggestions. I'll come up with something parallel or cache or something GPU. If there's something in particular people would like to hear about, I'll open up a post on Piazza later, sort of a course review. We only have 2 more lectures, really, looking at the rest of the semester. It's all final projects after that. Okay, we can do a bit on MPI. Sure. I'll take other suggestions as well. I can't say have a good weekend yet. see you Friday. Keep up on the homeworks. Please do the peer reviews. Keep chugging along on final projects.